3 days after the eruption of Mount St. Helens in southwest Washington state, imponderables dust the air like volcanic ash.
Mount St. Helens blew its top, and that ash cloud spread from Washington state across the Great Plains and even dimmed the skies as far east as the Great Lakes.
Something strange is happening deep beneath the Cascade Range, a major mountain range of western North America. Hundreds of small earthquakes shook the ground near Mount St. Helens. What began as background activity soon became a clear warning sign. Between January and March, more than 350 quakes were recorded. Most occurred near the volcano's northern flank, the same area that collapsed during the deadly 1980 eruption. But this is more than just seismic noise. Satellite images show the mountain is swelling again. A surface bulge is slowly growing, signaling that magma may be rising underground. This kind of uplift often ends in disaster. Magma builds pressure, cracking the earth as it climbs. The deformation is now measurable in centimeters and increasing weekly. Volcanic gas emissions have also spiked. Sulfur dioxide has tripled. Carbon dioxide and hydrogen sulfide are rising too. These are classic signs of an awakening magma chamber. When gases, earthquakes, and surface changes appear together, pressure is building below. Scientists say this pattern is familiar, but something about it feels different this time. If magma is forcing its way upward, the real question becomes, is this just Mount St. Helens or part of something bigger? In this video, we explore volcanoes, the hidden connections between them, and the unexpected dangers their eruptions could unleash. Before we start, make sure to like this video and subscribe to our channel. And now, let's dive in.
One geologist said today, there is no record in geology in the last 4,000 years of anything like this happening before.
Mount St. Helens awakens. Tucked into the rugged wilderness of Washington state, Mount St. Helens rises quietly among the peaks of the Pacific Northwest. But behind its calm appearance lies one of the most dangerous and closely watched volcanoes in the United States. It is best known for its catastrophic eruption in 1980, which flattened forests, unleashed massive mud flows, and left behind a vast crater where the summit once stood. Now, the mountain has started moving again. Not with an eruption, but with signals that can't be ignored. Seismologists have recorded nearly 350 earthquakes beneath the volcano in just a few months. Most of them are shallow, concentrated under the northern flank. That is the same area that gave way in 1980 during the most destructive volcanic event in U.S. history. The ground is changing shape. Satellite radar has detected uplift, slight but steady. Centimeters of upward motion are building quietly, week by week. That kind of deformation means magma could be rising. As molten rock accumulates, it forces the earth to bulge, pressing against the crust from below. But movement alone doesn't tell the whole story. Instruments are also picking up volcanic gas emissions. Sulfur dioxide has more than tripled in concentration since late 2023. This gas is one of the first signs that magma is nearing the surface. Alongside it, carbon dioxide and hydrogen sulfide levels are climbing too. These gases usually escape when magma rises, cracking through older rock. What is happening now looks eerily familiar to geologists. They have seen this combination of signals before: small earthquakes, swelling ground, and rising gases. Together, these signs often mark the early phase of a recharge, a process where fresh magma fills the chambers beneath a volcano. So far, there has been no explosion, no ash plume, no lava. But the warning signs are growing. Scientists monitoring Mount St. Helens are seeing rhythmic tremors underground. These low-frequency vibrations suggest magma is pushing through narrow cracks. It is not erupting yet, but it is not sitting still either. This is not the kind of change that happens overnight. Volcanoes can build pressure slowly, over months or even years. But the pieces are falling into place, just as they did in 1980. That event gave little warning before it reshaped the landscape and left a massive crater in the mountain's side. Today, monitoring technology is far more advanced. Networks of sensors track every vibration, every gas shift, every inch of uplift. Yet even with this technology, predicting the exact moment of eruption remains difficult. What scientists know for sure is this: something is moving deep below Mount St. Helens, and that movement is gaining momentum. Our team needs your help. Subscribe to our channel to help more people learn the truth about current events. And now, we move on. Yellowstone's strange behavior. While Mount St. Helens is rumbling in the Pacific Northwest, 560 miles to the east, another giant may be waking up. Yellowstone is no ordinary volcano. Hidden beneath the calm landscapes of Wyoming is a supervolcano capable of global devastation. But this time, its activity may not be rising in isolation. New research is raising serious questions. Could Mount St. Helens be stirring Yellowstone from afar? The first clues emerged as seismic swarms intensified beneath Mount St. Helens. Not long after, Yellowstone's own underground systems began shifting. Scientists observed an unusual surge in geothermal heat beneath the Norris Geyser Basin, one of the most thermally active zones in Yellowstone. Almost simultaneously, Steamboat Geyser, the tallest active geyser on Earth, broke eruption records, behaving more aggressively than ever. These are not just isolated flukes. Some eruptions at Steamboat have occurred in near synchronization with tremor clusters at Mount St. Helens. The odds of this being pure coincidence are shrinking. Experts are now examining whether both volcanoes might be linked through a shared network of deep crustal stress. Seismic arrays across Yellowstone have detected long-period earthquakes beneath Yellowstone Lake. These LP events are low-frequency signals caused by the movement of fluid, often magma, within the Earth's crust. They tend to appear before eruptions or hydrothermal explosions. At the same time, GPS monitoring has revealed uplift of the ground above the Yellowstone caldera. The crust is rising, slowly but steadily, pushed from below. All of this is happening while Mount St. Helens is showing signs of magma recharge. That matters, because some geophysicists believe that when a volcano begins to stir, it can transfer stress across tectonic distances. The Earth's crust is not a rigid shell. It is a fractured, shifting puzzle of plates and faults. A disturbance in one part of the system can affect another hundreds of miles away. Yellowstone is especially sensitive. Fueled by a mantle plume and sitting on ancient faults, its massive magma chamber is vulnerable to any regional pressure change. The idea is not that magma flows from St. Helens to Yellowstone, but that seismic waves and pressure imbalances might act like a trigger. In other words, Mount St. Helens might just be the spark. And that spark could light a fire under one of the world's most dangerous volcanoes. But before we dive deeper into this explosive story, please take a moment to hit that like button. It's a small action, but it helps YouTube's algorithm promote our videos to a wider audience. Are these volcanoes connected? At first glance, Mount St. Helens and Yellowstone seem worlds apart. One rises in the Cascades of Washington, the other sits in the heart of Wyoming. But beneath the surface, the Earth does not respect state borders. Instead, it operates as a complex, interconnected system of pressure, fractures, and deep magmatic reservoirs. Some scientists now believe that these two iconic volcanoes may be more connected than we ever imagined. The idea is simple, but the implications are huge. When one volcano starts to stir, it can shift the pressure balance across the region. This shifting stress may travel through deep fault zones and ancient magma pathways, disturbing other volcanic systems. In this view, Yellowstone might not need to erupt on its own. It could be nudged into action by the unrest happening hundreds of miles away. There is precedent for this. In 1992, a powerful 7.3 magnitude earthquake, known as the Landers Quake, struck Southern California. What happened next shocked scientists. Over 220 miles away, in the Long Valley caldera, seismic activity surged. Steam vents opened. The region's already active geothermal field became noticeably more restless. It was one of the first real-world cases where tectonic stress transfer over long distances seemed to awaken a volcanic area. Another example came in 2002, when a massive earthquake in Alaska's Denali Fault System appeared to influence volcanic systems across North America. In the weeks that followed, small swarms of earthquakes were detected in Yellowstone and other calderas. Scientists didn't declare a direct cause and effect, but the timing was hard to ignore. And in Iceland, volcanoes often show signs of synchronization. An eruption in one volcanic system has been known to influence pressure and behavior in another, sometimes dozens of miles away. The crust beneath these volcanoes acts as a network, not a wall. Now, researchers are re-examining the Cascadia region and its links to Yellowstone. New seismic tomography scans show deep fault structures stretching across the northwest. potentially allowing stress from Mount St. Helens to reach far beyond its immediate surroundings. If this theory holds, we could be watching a slow, invisible chain reaction already underway. The Earth's crust is not a single rigid shell. It is a cracked and shifting puzzle of tectonic plates, faults, and molten intrusions. In this setting, it only takes a small shift in one place to upset the balance elsewhere. Mount St. Helens may not be isolated in its awakening. It may be the first in a line of dominoes. Some scientists call this the Cascade Effect. One disturbance, passed from mountain to mountain, could build toward a much larger event. A spark in Washington might one day ignite a storm in Wyoming. Do you think it's possible for one volcano to trigger another from hundreds of miles away? Or are we just connecting dots that were never meant to form a pattern? Let us know what you believe in the comments. Share our new video on X to help us grow. Every share counts. The Cascade Effect. Far beneath the surface of the American West lies a tangled network of faults, fractures, and fossilized magma paths. These ancient geological structures, some formed tens of millions of years ago, may hold the key to understanding how one volcano could influence another. This concept, known as the Cascade Effect, is gaining attention among volcanologists. The idea is simple, yet alarming. When a major volcano like Mount St. Helens begins to recharge or erupt, it may send seismic and tectonic ripples across vast distances. These ripples can increase stress along connected faults, awakening distant systems. Not by moving magma directly, but by disturbing the delicate balance that holds them in check. One of the most dramatic examples came in 2008, when Chile's Chaitén volcano erupted unexpectedly after more than 9,000 years of dormancy. Within weeks, several other volcanoes along the Andean volcanic belt began showing increased seismic activity. Some produced ash plumes and small eruptions of their own. While scientists couldn't confirm direct causality, the clustering of these events sparked debate about long-range triggering mechanisms in volcanic arcs. In Iceland, similar patterns have been documented. Eruptions in one volcanic system have caused shifts in nearby calderas, suggesting that magma chambers may be more connected than once believed. The crust beneath these volcanoes acts more like a sponge of pressure than a wall of rock. Now, scientists are revisiting the ancient pathways buried between the Cascades and Yellowstone. Using seismic tomography, they've mapped out low-density zones and partial melt corridors that stretch for hundreds of miles underground. These are not solid tunnels, but weakened regions where stress and heat can move more freely through the crust. Yellowstone sits above a mantle plume, a deep column of rising magma that fuels its supervolcano. It is sensitive to even subtle changes in tectonic pressure. If Mount St. Helens continues to awaken, and if the regional stress patterns evolve in just the right way, it's possible that Yellowstone could begin to stir as well. It's not just theory anymore. The closer we look, the more we see patterns linking activity between volcanoes once thought isolated. The Earth is not a collection of independent systems. It's a living machine, where movement in one part can disrupt the balance in another. So here's the question. If these ancient corridors are still active, and if one eruption really can set another in motion, are we watching the first domino fall? Let us know what you think in the comments. Could a reawakening in the Cascades lead to a chain reaction that shakes the entire continent? Warnings from above and below. As Mount St. Helens rumbles back to life, Yellowstone is sending its own signals. Some blast skyward through steam and geysers, others pulse quietly from deep beneath the surface. Scientists have long monitored these volcanic giants, but the recent combination of surface eruptions and underground tremors is raising new concerns. Could both sites be responding to the same growing instability? At the center of this concern lies Steamboat Geyser. Located in the Norris Geyser Basin, it is the tallest active geyser in the world. Since 2018, it has erupted with record frequency, but its recent behavior appears to be shifting once again. Steam discharges are becoming more intense, and the time between eruptions has shortened. These changes accelerated just as Mount St. Helens began showing signs of magma recharge. The timing is suspicious. The system may be under stress. While Steamboat erupts with dramatic flare, what is happening beneath Yellowstone Lake is even more unsettling. This massive body of water sits atop one of the most seismically active zones in the region. Deep below the lakebed, sensors have detected a rising number of long-period earthquakes. These are low-frequency tremors that often indicate fluid movement in magma systems. They are not the result of surface activity. They suggest internal pressure is building and shifting rock below. Adding to this picture are satellite measurements showing steady uplift in parts of the caldera. The ground is slowly but measurably rising. This deformation is not just background noise. It is one of the earliest signs of volcanic reactivation. Uplift like this shows that something beneath the crust is pushing upward, likely magma under pressure. What makes these signals more concerning is the broader context. These changes in Yellowstone's behavior began to pick up shortly after the seismic swarm at Mount St Helens. That may not be a coincidence. Geologists believe stress released in one region can transfer across tectonic structures. In other words, when one volcano stirs, it can disturb others. Yellowstone and Mount St Helens may be separated by hundreds of miles, but they sit on a connected geological canvas. Ancient fault lines, magma pathways, and regional pressure systems link them more closely than distance might suggest. What begins as a local event can ripple outward, disrupting fragile balances far from the origin. It is possible that Mount St Helens has already passed the signal eastward, a nudge in the tectonic system that is now being felt across the Yellowstone region. These events may not be isolated. They could be stages in a larger sequence, unfolding step by step. What do you think? Could Steamboat's violent sprays and the tremors under Yellowstone Lake be early warnings? Are we watching the same story unfold in two different places? Let us know your thoughts in the comments. What if Yellowstone erupts? Beneath Yellowstone's peaceful scenery lies one of the most dangerous forces on Earth. This supervolcano holds enough energy to reshape continents and plunge the world into chaos. If it erupts, the effects would be immediate, devastating, and far-reaching. And now, with Mount St Helens showing renewed activity, the threat feels closer than ever. The eruption would begin with a series of violent blasts. Pyroclastic flows moving at hundreds of miles per hour would obliterate everything within a 100-mile radius. Towns like Bozeman and Jackson Hole would be reduced to ash in minutes. The immediate death toll could reach 90,000 people. Millions more would be at risk as infrastructure collapses, power grids fail, and emergency services break down. Then comes the ash. Columns of volcanic debris would rise into the stratosphere and spread across the globe. In the United States alone, more than 10 million people could be displaced. Ashfall would coat cities, block roads, poison water supplies, and cause roofs to collapse. Air traffic would grind to a halt. Farms would shut down. Clean water would become scarce. The economic impact would be unlike anything in modern history. FEMA has estimated that a full Yellowstone super eruption could cause up to $3 trillion in damage, roughly 16% of the entire US GDP. That is up to 50 times more damage than Hurricane Katrina, which caused around $190 billion in losses when adjusted for inflation. The eruption would instantly trigger a national crisis and a global economic shock. But the danger doesn't stop there. Ash in the upper atmosphere would block sunlight, causing a sudden drop in global temperatures. This is what scientists call a volcanic winter. Crops would fail across continents. Livestock would die. Food prices would skyrocket. Famine would spread in vulnerable regions. In the worst-case scenario, parts of the planet could see years without a real summer. Weather patterns would shift unpredictably. Droughts, floods, and storms would increase in intensity. Forests would die back. Rivers could dry up or flood at the wrong times. The balance of entire ecosystems would collapse. Global food production could fall by half or more within the first 2 years. Even a smaller eruption would still be catastrophic. Ash could cripple multiple states, damage power infrastructure, and contaminate rivers. The chaos would ripple through every part of American life, from transportation and healthcare to banking and energy. Recovery would take decades. And here's the part that ties it all together. Some scientists believe Mount St Helens may already be transferring tectonic stress eastward. If one volcano is waking up, it might only be a matter of time before another follows. Do you think America is prepared for this level of disaster? What would you do if Yellowstone erupted in your lifetime? Share your thoughts in the comments below. Scientists are watching. We cannot stop volcanoes, but we can try to understand them. Today's scientists are more equipped than ever to track the warning signs of a disaster before it strikes. At Mount St Helens and Yellowstone, a network of high-tech instruments now scans for every possible clue of volcanic unrest. Because when the ground starts to stir, time becomes our most precious resource. It starts with vibrations. Seismometers planted deep in the soil measure even the smallest tremors. Some of these are barely strong enough to register, but when they repeat or cluster, they can reveal magma shifting underground. These tiny movements often come before larger quakes or eruptions, acting like whispers from the Earth's core. Next comes the ground itself. GPS stations and satellite interferometry measure uplift with astonishing precision. If the crust begins to bulge even a few centimeters, scientists take notice. At Mount St Helens, this ground swelling was the first visible sign before the 1980 eruption. Now, similar instruments track Yellowstone's caldera for the same early signals. Then there are the gases. Volcanic systems release sulfur dioxide, carbon dioxide, and hydrogen sulfide when magma rises. Sensitive gas detectors can measure changes in concentration in real time. A sharp increase might mean the pressure below is building rapidly. And when gas levels rise at the same time as seismic activity and uplift, the pattern becomes clear. Something is moving underground. Thermal cameras and satellite infrared scans complete the system. These tools detect heat anomalies, highlighting areas where magma may be nearing the surface. Hotspots that appear suddenly or expand quickly are taken as serious warnings. Combined, these data streams paint a detailed picture of the volcano's behavior. At the heart of all this is the USGS and its partner institutions. From the Cascades Volcano Observatory to Yellowstone's dedicated research stations, teams of geologists, volcanologists, and engineers work around the clock. They cross-check data, model eruption scenarios, and alert the public when thresholds are crossed. But the signals are not always obvious. Magma can shift without warning. Gases may leak slowly for months. Some eruptions come with fanfare, others without a sound. That is why monitoring must be constant, and decisions must be fast. Every delay increases the risk. And with Mount St Helens showing signs of reactivation, Yellowstone's network is now being watched with renewed urgency. The two volcanoes may be far apart, but the systems tracking them are linked. The science is improving, but the danger has not gone away. If we miss even one signal, the consequences could be devastating. Do you think we're doing enough to stay ahead of these threats? Or are we still one step behind nature's next move? Let us know what you think in the comments. Can we predict eruptions? Today, we can track volcanoes more precisely than ever before. Across the United States, a network of advanced sensors constantly monitors seismic tremors, gas levels, and ground movement. From Mount St Helens to Yellowstone, satellites and ground stations are scanning for changes that might signal an approaching eruption. Seismometers buried deep in the earth detect the faintest vibrations, often before people even feel them. Some of these tremors are harmless. Others are harmonic tremors, rhythmic vibrations that suggest magma is moving upward through cracks in the crust. When these patterns emerge near active volcanoes, scientists begin to pay close attention. Gas sensors track emissions like sulfur dioxide and carbon dioxide. A sudden spike can mean magma is rising closer to the surface. Ground-based interferometric radar helps measure deformation, the slow swelling of land that occurs when pressure builds below. These tools give us clues, but they do not always provide certainty. Volcanoes are complex. They do not erupt on a schedule. Machine learning and computer simulations are now part of the toolkit. These systems process massive data sets to identify early warning signs and simulate eruption scenarios. Yet even with all this progress, questions remain. Are we truly ready? And can we always trust the signals? To answer that, we must look at the past. In 1980, Mount St Helens gave warning signs: earthquakes, steam explosions, a growing bulge on its northern flank. Scientists raised alarms, and evacuations followed. Still, when the eruption came, it was far more violent than expected. The blast killed 57 people and leveled hundreds of square miles of forest. In 1991, Mount Pinatubo in the Philippines began rumbling weeks before it erupted. This time, a coordinated effort between scientists and authorities led to one of the most successful evacuations in volcanic history. Over 75,000 people were moved out of danger. The eruption destroyed homes and farmland, but thousands of lives were saved. Then came 2010. The Icelandic volcano Eyjafjallajökull, meaning Island Mountain Glacier, began to shake. Its eruption sent ash clouds across Europe, grounding more than 100,000 flights and disrupting travel for millions. Here too, seismic and thermal warnings were present, but the global impact was far greater than expected. These examples show that predictions can work, but they require attention and swift action. Today, as we see Mount St. Helens recharging and Yellowstone acting strangely, the question becomes more urgent. Are these signals isolated, or is there something deeper at play? What do you think? Do you believe modern science can truly warn us before the next big eruption? Share your thoughts in the comments and let us know if you trust the signs. Fleeing wildlife. Something strange is happening in the forests around Mount St. Helens. Local residents have reported an eerie hum, a sound that seems to rise from the ground itself. It is not loud, but it is constant. A deep, pulsing vibration like a distant engine echoing through the trees. This phenomenon is known to scientists as low-frequency tremor, and it is one of the most unsettling signs of volcanic unrest. Unlike sharp, sudden earthquakes, these tremors are rhythmic and sustained. They suggest that something fluid is moving beneath the surface. In volcanic systems, this often means magma is pushing through cracks in the crust. These vibrations are especially dangerous because they indicate ongoing pressure changes rather than a single isolated event. Animals are noticing the change too. Flocks of birds that once filled the sky near the volcano have vanished. Herds of elk that used to graze calmly at the mountain's base are now retreating into distant valleys. Even smaller animals seem restless. Rabbits, squirrels, and foxes are acting erratically, fleeing areas they usually call home. Scientists have long believed that animals can sense danger before humans can. They might detect changes in the Earth's magnetic field, or subtle shifts in air pressure. In past eruptions around the world, wildlife behavior has served as an early warning. At Mount Pinatubo in 1991, and again in Japan's Mount Ontake in 2014, animals were seen fleeing the area days before the eruption began. What is unfolding now at Mount St. Helens feels similar. Motion-activated cameras set up by researchers have captured elk moving in tight herds at unusual hours. Bird migration patterns have shifted weeks ahead of schedule. Some nests have been completely abandoned. These behaviors are not random. They point to something underground, something the animals seem to understand instinctively. The tremors themselves are not new, but their pattern is changing. Seismologists have identified what are called harmonic tremors, continuous vibrations linked to magma movement. These signals are being picked up by seismic arrays placed throughout the Cascade Range. The longer they last, the more likely it is that molten rock is on the move. At the same time, monitoring teams have recorded bursts of gas release that align with periods of stronger tremor activity. It is as if the Earth is exhaling under pressure, releasing energy in cycles. These patterns are consistent with a volcano that is not sleeping, but stirring. When animals flee and the ground begins to hum, history has shown us that it is time to pay attention. Nature often speaks before disaster strikes. While science gives us data, wildlife gives us instinct. And right now, both are pointing in the same direction. Have you ever witnessed animals acting strangely before a storm, an earthquake, or something unexplained? Do you think wildlife can detect threats we still don't understand? Share your thoughts in the comments below. Science versus fear. We live in an age of sensors, satellites, and supercomputers. Scientists today have more tools than ever to monitor the ground beneath our feet. They can detect the slightest tremor, the faintest gas emission, or the smallest bulge in the Earth's surface. Volcanic risk is no longer a mystery. But despite all this, one question still haunts us. How much can we really predict? Yellowstone, Mount St. Helens, and the vast volcanic systems of the western United States are under constant surveillance. Networks of GPS sensors track every shift in the crust. Satellites use radar to detect ground deformation with millimeter precision. Seismic arrays listen for the deep groans of magma on the move. And yet none of these tools can offer certainty. That is where science meets fear. We can measure, we can model, we can issue warnings, but we cannot control what happens next. Nature does not follow our timelines or respect our expectations. It builds pressure in silence, only to release it when we least expect. Some volcanic eruptions are preceded by weeks of warning signs. Others erupt with little or no notice at all. The 1980 eruption of Mount St. Helens gave scientists only a few days of clear signals. The Chaitin eruption in 2008 took the world completely by surprise. And a future Yellowstone eruption, while statistically unlikely in our lifetime, remains a possibility that cannot be ruled out. In 2014, a video of bison running along a road in Yellowstone went viral. Millions watched and assumed the animals were fleeing an impending eruption. Panic spread fast. News outlets picked up the story. But the truth was simpler. The animals were simply moving as they do every spring. The USGS confirmed there was no unusual volcanic activity at the time. Yet the public had already latched onto fear. This uncertainty fuels anxiety. Sensational headlines spread faster than facts. Some people dismiss the risks entirely. Others panic at every tremor. The truth lies somewhere in between. We must respect the threat without succumbing to fear. We must listen to what the Earth is telling us, even when it whispers. Scientists are not in the business of fear. They are in the business of understanding. But part of that work means acknowledging what we do not yet know. There is still much to uncover about how volcanoes interact, how stress travels underground, and how supervolcanoes evolve over time. For now, we watch, we measure, we prepare, and we continue to ask the hard questions. Not because disaster is guaranteed, but because silence is not safety. What stirs beneath the surface may sleep for centuries, or awaken tomorrow. So we ask you, do you trust the science to keep us safe, or do you think nature is still one step ahead? Share your thoughts with us in the comments. Thank you for exploring the hidden corners of the USA with us. Click on the video you see on the screen to check out other hidden discoveries on our channel.